The Standard Model has been one of the most successful theories that scientists have come up with to describe the fundamental nature of the universe. We start the video off with fermions. Fermions are matter particles that constitute everything we know of in the universe, except for dark matter. They consist of two main families, the quarks and the leptons, each of which are further categorized into three generations of matter. We have the up and down, charm and strange, and top and bottom quarks. The notable pattern among them is the charges of this row of particles is 2/3, while the bottom row is 1/3. Then we have the electron, muon, and tau leptons, each of which has a neutrino counterpart that is also categorized as leptons. These leptons have a charge of -1 and a lepton number 1, while the neutrinos have 0 charge and lepton number -1. Quarks are the particles that make up other particles, like the proton and the neutron, which consists of up-up-down and up-down-down respectively. Each of these fermions have antimatter counterparts, which are particles with the same properties except opposite charge. Bosons are force carriers of the four fundamental forces. Here they have been ordered in strength. We have the gluon, which is the carrier of the strong nuclear force, which is the force that holds quarks together to form hadrons, and the force that binds protons and neutrons together to form an atomic nucleus. This acts on quarks and gluons. Then we have the photon, which is a force carrier for electromagnetism. It interacts only with charged particles. We have the W and Z bosons, which are mediators of the weak nuclear force and acts within nucleons as it mediates particle decay. This interacts with fermions. Lastly, we have the graviton, which is a theorized force carrier for gravity and acts on all particles. We haven't been able to experimentally find it yet, but in order for the Standard Model to work, we expect that this exists. The gluon, the W and Z bosons act on very tiny ranges, while the photons and gravitons act on an infinite range of distance. However, we're not actually done yet because there's also the Higgs boson, the carrier of the Higgs field that gives mass to other particles. The Higgs boson, like the graviton, remained theorized for a very long time until it was experimentally found in 2013. If you're wondering where the names fermion and boson comes from, it's the mathematical principles and rules they follow. Bosons follow the Bose-Einstein statistics, and fermions follow the Fermi-Dirac statistics. These mathematical principles essentially dictate how the fermions and the bosons interact between each other and within their groups. All of these subatomic interactions must follow a few conservation laws, such as charge, mass, energy, and lepton number. As a side note, there's also parity symmetry, where you expect laws of physics to remain invariant or the same when physical space is mirrored, but in fact, the weak force, and only the weak force, violates this. In terms of particle classification, because of quark confinement, quarks can't exist by themselves. So the standard classification generally consists of leptons and hadrons, which are further broken down into mesons and baryons. Mesons are a quark-antiquark pair, and baryons are made up of 3 quarks. There are certain rules that these hadrons must follow, such as their charge must add up to whole numbers. There are many interesting phenomena that stem out of the Standard Model. For instance, we have pair production and annihilation, where a quark and antiquark pair is produced via the mass-energy equivalence principle from a neutral boson, and can also come together and annihilate to produce energy. We also have an imbalance between matter and antimatter in the universe. There are some theories and possible explanations why this is the case, like CP violation, where scientists have observed that certain hadrons do not obey parity conservation like they originally thought. Much of the math patterns and structures in the Standard Model are still unknown or unexplained, like why we have 3 generations of matter, and of course the glaring elephant in the room, the graviton. Dozens of theories, called grand unification theories, try to unite the graviton with the rest of the Standard Model, but all seem to not have much experimental success. Thanks for watching.